This video is for Edexcel GCSE Chemistry Unit C1 Topic 5. So this is all about fuels. It's quite a long topic. It's right at the end of the C1 unit, and it covers topics such as crude oil and the hydrocarbons that make up crude oil, the fractions that are actually within there, alkanes, alkenes, cracking, polymerisation, but also the issue with fuels, alternatives to some of these fuels that we get from crude oil. So let's start off with crude oil. Crude oil is made up of hydrocarbons. So the crude oil itself is made with different size hydrocarbons. These different size hydrocarbons, okay, so it's made of different size hydrocarbons. These different size hydrocarbons, they contain hydrogen and carbon only. I want to make that point very, very clear. Hydrocarbons only contain hydrogen and carbon. That's 2 marks. One for saying it contains hydrogen and carbon, the second mark for saying it only contains them. So petrol and diesel are examples of hydrocarbons. They contain only hydrogen and carbon. Cannot stress that enough. So crude oil is a mixture of these hydrocarbons. They have different lengths, so each of them has different properties. They have individual properties. The key property though is boiling point. They all have different boiling points, and that allows them to be separated easily. We'll go through that separation process in a second. Alright, before we do that though, I shall talk about each of the uses and how we actually use each of them. So bottled gas, that's the top one. Refinery gas, or just gas, is used in domestic heating and cooking. So like when you use gas on a barbecue, that's the gas you're using there. Petrol is used for cars, obvious one. Kerosene, jet fuel, as I like to say in class to help people remember that, that's aircraft fuel. Diesel oil, that's used for fuel for some cars and trains. Fuel oil, that's large ships and stations. Bitumen is the residue in the diagram that's at the bottom over here. That's used to surface roads. So petrol, kerosene, and diesel are non-renewable fossil fuels obtained from crude oil, and methane is a non-renewable fossil fuel found in natural gas. There is one more, and it's called naphtha. That's over here, and that's used for making chemicals, but these are the ones that I like to ask about most in the exam. So each of these hydrocarbons differs the number of hydrocarbons in the molecules. So gas has fewer hydrocarbon molecules than bitumen. Okay, it's boiling point. Low boiling point, high boiling point, high boiling point. How easy it is to light, easy to light, not easy to light. How viscous it is, so it flows easily, in other words, not very viscous, very thick, it does not flow easily. Right, so to explain how this is separated out, each of these fractions has a different boiling point, so as you heat up crude oil, each fraction will come off at a separate temperature. So first refinery gas comes off, okay, then petrol at a slightly higher temperature, naphtha at a slightly higher temperature, kerosene at a higher temperature, diesel oil at a higher temperature, fuel oil at the highest temperature that they actually use in this process, and anything that's left is what they call bitumen. Right, let's move on. So once we have these fuels, we can heat them, so we can burn them. Burning is a scientific word for burning, and we call that combustion. There are 2 types. Complete, that's where there's lots of oxygen, and incomplete, so that's where there's not so much oxygen, where there's a lack of oxygen. So complete combustion, you always get this process taking place. Hydrocarbon plus oxygen equals carbon dioxide plus water plus energy. That's the process that happens. So carbon and hydrogen within the oxygen have been oxidized. Within the oxygen have been oxidized. Within the oxygen side, it's okay. Within the hydrocarbon, sorry, I should say. So the carbon and the hydrogen within the hydrocarbon have been oxidized. So both of those have been oxidized because the carbon becomes carbon dioxide and the hydrogen becomes water. The waste products in this reaction are completely harmless. Water, carbon dioxide, harmless. Here is an example reaction for hydrocarbon and methane, and it's balanced. Okay, big tip with balancing equations. More often than not on GCSE papers, the number that you have to chuck in front is usually 2. It just seems to be the way that they usually give the formulas that they give. Remember, always check to see how many there are on each side and then put the number in. There's plenty of videos on balancing equations on YouTube. Incomplete combustion, that's when there's not enough oxygen. So because there's not enough oxygen, you don't get as much carbon dioxide as you did before. You still get carbon dioxide. You also get carbon monoxide, that's CO rather than CO2, carbon monoxide. and you get carbon. So that's like the sooty stuff that's left behind. You still get water, still get energy. So if there's not enough oxygen present, this is what happens. You get a smoky yellow flame, less energy given out. So carbon monoxide is also dangerous. It's colourless and odourless, and it's a toxic gas. So if you've got a faulty gas boiler, it can actually lead to death. Or if you've got a blocked chimney, it can lead to death, because incomplete combustion will take place. So here's a formula for it, for methane again. And you can see there's your carbon, sooty stuff. There's carbon monoxide, that toxic gas. You can see carbon is also produced in incomplete combustion. Like I said, that's the sootiness that's left behind. Right, so there are some problems with fuels. So the two main problems with burning fuels are sulfur dioxide, which leads to acid rain, and carbon dioxide, which is a greenhouse gas, which essentially therefore leads to global warming. Sulfur dioxide mixes with clouds to form dilute sulfuric acid. Okay, that falls as rain, acid rain, and that can go into lakes and kill plants and animals. It can also damage limestone buildings, and acidic reaction essentially takes place there, chemical reaction. Agreements have been put in place to try to limit the amount of sulfur dioxide that's actually released. It can be removed before we actually burn the fuel, but that's an expensive process. It takes a lot of energy, and it's usually produced from burning more fuel, so it's just a roundabout cycle of doing that. Recently, there's low versions of petrol, low sulfur versions of petrol and diesel have been developed. So, and also power stations have acidic gas scrubbers that remove harmful gases before they're released into the atmosphere. So in other words, using things like calcium carbonate and limestone calcium sulfate as part of this reaction, because remember, calcium carbonate can neutralize acidic substances like acidic soil. Catalytic converters in cars clean up the exhaust fumes, and so the government is trying to reduce the amount of fossil fuels that actually use an attempt to reduce the emissions from these. Carbon dioxide is the other dangerous gas. Methane and water are also included in this process of greenhouse gases there. They act as a sort of insulating layer around the Earth. They prevent any heat from actually escaping the Earth that's actually been absorbed by it. So they absorb the heat energy that would normally escape to space and send it back down to Earth, so they re-radiate it back to Earth. They will, in all directions, but some of that is that back to Earth. So instead of just escaping up to space, at least half, as a minimum, gets re-irradiated back. Human activity can affect the amount of carbon dioxide in the atmosphere. Obviously, burning fossil fuels releases some as well, but also the use of petrol and other processes, creation of concrete, releases large amounts of carbon dioxide. Burning trees release carbon dioxide. Microorganisms also release carbon dioxide. Living trees taking carbon dioxide via photosynthesis. So these trees, sort of are carbon neutral. They usually, if you remove these trees, you're actually removing organisms that are taking carbon dioxide out of the atmosphere. So that's quite a difficult thing to replace. Scientists have been trying to limit the amount of carbon dioxide in the atmosphere. So there's two major techniques they're doing. Ion seeding. Ion seeding promotes growth of phytoplankton, which perform photosynthesis. So these plankton will photosynthesize and take in carbon dioxide. There's no real way of controlling which plankton grow. Some plankton are toxic. Dead plankton can use up oxygen. That could then lead to areas of oceans becoming inhospitable. And you learn a bit more about what happens when you have dead organisms a bit later on when we do eutrophication in biology. Converting carbon dioxide to hydrocarbons is the other one of them. Several methods are being tested, including high pressures, high temperatures, and metal catalysts, but they need high amounts of energy to work, and these energies need to be produced from green fuels, not fossil fuels, if we're going to limit the amount of greenhouse gases emitted. So, good fuels. We've got all these options for fuels. What makes a good fuel? How easy it is to light. You want a fuel that is very, very easy to light. It burns very easily. You want it to have a high energy value, so for a very small amount of mass, you want it to give out quite a lot of energy. You want a lack of ash and smoke. You don't want any waste being left behind, and you want it to be easy to store and transport. So gas and oil leaks can be dangerous. Coal is therefore really easy to transport, because if you drop a lump of coal, it's just going to be a lump of coal. It's not going to leak out in such a way, such as gas, which is flammable, or oil, which could cause spills. Biofuels are alternatives to fossil fuels. They're made from chemicals obtained from living organisms. The two main biofuels are ethanol and alcohol. Biogas is made from organisms as they decompose waste. This gas can be burnt or combusted to boil water, turn steam, generate electricity. Same ideas we learned about in physics. It's renewable, and the plants that are used to produce biogas took in CO2 from the atmosphere, so it's not adding any CO2 to the atmosphere that wasn't already there, it's just giving out what it already had. It's also a clean fuel, doesn't produce many particles, so not much waste like ash or soot. And the raw materials are cheap and readily available. Okay, so not much ash and soot, it's cheap and readily available. Ethanol is made from cane sugar, so yeast is used to ferment these sugars. Cars can now run on 90% petrol, 10% ethanol, so that's called gasohol. But large amounts of land are actually required to grow the amount of crops needed to produce the ethanol that is currently in demand. So if we're reducing land for other food production, we could end up with a food shortage. So gasohol instead of petrol will lead to less crude oil being used, but then distilling the ethanol itself actually requires energy, but it's also taking up extra land as well. So there's a bit of a balancing act to do there. So there's also the option of fuel cells. Fuel cells are simple. They take hydrogen and oxygen and form water from it, and that releases energy. And that can be used for everyday life. Hydrogen fuel cells are more efficient than power stations at producing electricity, so a lot of energy is not being wasted. However, hydrogen is a gas that takes up a large volume, it's difficult to store, and it's also explosive. Hydrogen fuel is often made from fossil fuels, which again demonstrates this reliance on fossil fuels that we have. So, anytime we think about this process, they need some energy, where do you get that from? Always from fossil fuels. So we're stuck in this cycle until we can really crack renewable energies. We're not going to get past it. So all of these alternative fuels still in some way require us to use fossil fuels as things stand. So we spoke about energy content from fuels. We spoke about the fact that what we want to know is that we want a fuel that needs a small amount of mass to release a large amount of energy. So how do you actually measure that? What if you get two say cups, both of them insulating, so they're not losing the heat, and the heat that is coming from the fuel goes directly into this cup, and they're at the same starting temperature, and you start with the same mass of fuel, and you have the same volume of water in there. Actually, you don't start with the same mass of fuel, you start with the same volume of water. What you do is you burn the fuel, you raise the temperature of it, say 10 degrees, and then you measure the mass of fuel that did that. You do the same for your other fuel. And what you do is you compare your values of mass lost. Whichever one used less mass to raise it by 10 degrees was the most efficient fuel. The only thing you've got to watch for is not all of the energy from the flame, not all of that heat energy from the flame will go directly to this cup. Some will be lost to the surroundings. It's always initial mass of that fuel burner. Take away the final mass of that fuel burner to tell you how much has actually been lost. So this takes us on to alkanes and alkenes. Alkanes and alkenes are two types of hydrocarbons we need to know about. Alkanes, note a single E, are saturated hydrocarbons. They have all single bonds. No spare bonds, all single bonds. So alkanes are saturated hydrocarbons. This means they cannot form polymers. Okay, we'll do a bit more about polymers in a second. You need to know how to test for these. So to test for an alkane is to use bromine water. It will not change colour. It will start brown and it will end brown. Okay, so that's what will happen. It will start once you add bromine water. Your bromine water will come in brown and it will stay brown. You need to know the formula and structure of the first three alkanes. So that's shown over here. Scroll back up slightly so you can see them clearly. The general formula for an alkane is CnH2n plus 2. So what that means is for however many carbons there are, you times it by 2 and add 2 to figure out how many hydrogens. So methane, ethane, propane. There's a way of remembering the first 4, which I use to help me remember the first 3, and that's many elephants prefer butter. Let's forget about butter and remember these 3. They have to remember that order. Remember, each carbon must have 4 lines coming off it, and each of those lines links to a hydrogen. And we've got that for the first 3 there. Alkenes, they are hydrocarbons with one or more double bond. This means that they are unsaturated because they have these spare bonds because they have a double bond. Alkenes can form polymers by opening up that double bond. So when we get to polymerization, what happens is this bond over here opens up and allows connection to another. Again, it's the same test as before. You're adding bromine water to it, but this time, instead of staying brown, it will go colourless. You need to know the structure of the first two alkenes. That's shown to the left over here. The general formula is CnH2n. So how many carbons, you times that by 2, that's how many hydrogens you have. So because there's got to be a double bond between the carbons, many or methene doesn't exist. Okay, it goes with ethene and propene. So it's the second one and the third. Remember there's a double bond between the two carbons, and remember there is a double bond here, and then it goes off at an angle for the rest of them. Cracking. So you've got to memorize these 5. Make sure you can draw them. Make sure you know the formulas. Make sure you know the names. Alkenes, 2Es, double bond. I must have remember that one. Cracking. Oops, just gone a bit too far. Cracking is a thermal decomposition reaction. Okay, it's a process of splitting up a large hydrocarbon chain. Long hydrocarbon chains aren't very useful, so making them into smaller chains makes them into more useful hydrocarbons. So it's taking a long hydrocarbon chain and splitting it into alkanes and alkenes that are shorter. So here's definition straight from the specification. So this, literally straight from the specification. So if you quote this in an exam as a definition of cracking, you'll knock it out of the park. Cracking involves the breaking down of larger saturated hydrocarbons, molecules like alkanes, into smaller, more useful ones, some of which are unsaturated alkenes. The rest of them will be alkanes. Okay, so it doesn't say that there, but that is the case. Cracking is a form of thermal decomposition, just like I said, just like we learned about with the carbonates, because it involves breaking things down using heat. Most of the longer molecules produced in fractional distillation of crude oil are cracked into smaller molecules, such as petrol, because of the high demand for things such as petrol and not so much for things like bitumen. So cracking paraffin in a lab. So paraffin is a long hydrocarbon and we can crack it. There is mineral wool that's soaked with liquid paraffin. So as you sort of heat it up, that will become a gas. It passes over this porcelain gas, which acts as a catalyst in this reaction. That gas then goes down the pipe, bubbles through underwater, and you get it produced in this test tube. So you can actually see how many alkanes and alkenes you're producing. So what's actually happening chemically? Well, there's your paraffin. Okay, you're splitting it into octane, that's useful for petrol, and 2 ethene molecules as part of this. Okay, so you've got an alkane and 2 alkenes. Polymerisation is the opposite of this process. So that's joining together many monomers to make a polymer. Monomers are small molecules. Joining many ethene molecules together makes polyethene, or polyethene as it's also known. And this is the process here. So you've got a large number of these ethene molecules come together. You see double bond unfurls, double bond opens up, and you end up making polyethene or polythene from it. Polythene is stretchy and light, so it's useful for bags and hose pipes, laminating paper, and things like that. If you have many propene molecules together, you'll have polypropene. Polypropene is tough and flexible, so plastic containers. The book boxes that we have at my school, those are made of polypropene, so you can actually store the books in them, and they're waterproof, and if you drop it, it won't break. Some thermal underwear and carpets is actually made of polypropene as well, because of its strength properties and its flexible properties. If you joined many chloroethene molecules together, you would have a polymer called polychloroethene. That's PVC. That's resistant to wear, and it can be used to make clothing and electrical cabling, as well as pipes. Tetrafluoroethene polymerizes to polytetrafluoroethene, PTFE. It's really unreactive. It's flame resistant and resistant to wear. So that's what the non-stick coatings on pans is. In other words, Teflon. So you can see that each of these different polymers has a different use. Most polymers don't rot, they don't biodegrade. So that means they can't be broken down by microorganisms. This means that they'll contribute to landfill. So what's another solution? We'll burn them. If you burn them, you give off toxic gases. So they're difficult to dispose of. The best thing to do with plastics is to recycle them, okay, and use less. This is why we have the carry bag charge now in the UK. Using less of them means that we won't get so much landfill. This reduces the amount of fossil fuels being used up. However, due to the fact that there are so many different types of plastic, they all need to be sorted before they can be recycled, and that's an expensive process. Biodegradable polymers have recently been made. Polyethylene bags have been produced containing starch grains, and these break down. These bags have been broken down by microorganisms. And also, some plastics have been made that break down in sunlight, and these are often used in agriculture, so they can tip out everything they need the bag stays out there, and over a month or so period, or 2-month period, the bag biodegrades as well. And that is the end of C1 topic 5 for Edexcel GCSE Chemistry, and that is the end of the Edexcel videos for GCSE Chemistry as well, all for C1. Thank you and good luck.